Welcome back to Astronomy Daily, your go-to podcast for all the latest happenings in our incredible universe. I'm Anna.
And I'm Avery. We've got a big episode lined up for you today, packed with some truly fascinating cosmic updates.
That's right, Avery. We'll be diving into new research about lunar seismic activity and what moonquakes could mean for future bases on our nearest celestial neighbor. Turns out the moon is a lot shakier than you might think.
And speaking of drama, we'll also explore the explosive end of a massive star that had a very close encounter with a black hole. It's a story straight out of a sci-fi movie, but it's real.
Plus, we're tackling some long-standing cosmic mysteries, from the curious case of the universe's missing sulfur to groundbreaking new insights about Vesta, one of the largest objects in the asteroid belt, which might be more than just an asteroid.
So buckle up, because we're about to take a tour through the latest and greatest in space and astronomy news.
All right, let's kick things off with some big news about our own moon. We often think of it as a quiet, unchanging place, but new research is challenging that idea, especially when we consider building long-term bases there.
That's right, Anna. It turns out our lunar neighbor is more seismically active than many might assume. A recent study focusing on the Lee-Lincoln Fault in the Taurus Littoral Valley, where the Apollo 17 astronauts landed in 1972, highlights that these moonquakes could pose significant risks to future permanent lunar structures.
This research, led by Smithsonian Senior Scientist Emeritus Thomas R. Waters, emphasizes that the global distribution of these young thrust faults and their potential to still be active needs to be seriously considered. We're talking about planning locations and assessing the stability of any permanent outposts on the moon.
And the evidence isn't new. It's based on moonquakes in the region over the past 90 million years. Much of this evidence comes from material gathered by the Apollo astronauts themselves. Things like chunks of rocks and landslides are silent but clear proof of the power of even magnitude 3.0 quakes to shift surface materials around. It really points to the moon still being geologically active.
It makes you wonder, why does the moon even have quakes? Here on Earth, we're very familiar with earthquakes, primarily caused by plate tectonics and volcanic activity. Think of the San Andreas Fault or the Ring of Fire. Magma movement also causes tremors, like the recent events in Hawaii and Iceland.
But the moon operates differently. Its quakes are most likely caused by two main factors: Earth's tidal pulling and the moon's continuous cooling and shrinking. The deep moonquakes, occurring hundreds of miles inside, are due to Earth's gravity pulling on her satellite.
And the weaker quakes closer to the surface are generally attributed to the moon's gradual cooling and shrinking. Since its formation billions of years ago, the moon has actually lost about 150 feet of its diameter. There are also minor tremors from meteoroid impacts or surface rocks reacting to heating and cooling from the sun. So it's a world that's constantly shaking.
When we talk about the risks to future bases, it becomes quite significant. Short-term missions like the Apollo landings, where astronauts were on the moon for less than 2 weeks, didn't face much danger. But for permanent bases, the chances of damage during a quake go up simply due to the extended exposure.
Nicholas Schmurr put it into perspective. He said, if astronauts are there for a day, they'd just have very bad luck if there was a damaging event. But if you have a habitat or crewed mission up on the moon for a whole decade, that's 3,650 days times 1 in 20 million, or the risk of a hazardous moonquake becoming about 1 in 5,500.
He likened it to going from the extremely low odds of winning a lottery to the much higher odds of being dealt a four-of-a-kind poker hand. It really illustrates how much the probability increases over time.
And it's not just habitats. Countries like Russia, China, and the US are planning to put nuclear power plants on the moon. These facilities would supply massive amounts of power, but they'd also be susceptible to quake damage. This means any construction will need tough safety margins and shouldn't be located near active fault lines.
Which is a tall order considering how many fault lines thread through the moon. That's why this study of lunar paleoseismology, looking at evidence of past quakes, is so crucial. It will help us chart the safest places to build these long-term habitats and power plants. It's all about understanding our cosmic neighborhood, before we make ourselves at home. From lunar shaking, let's zoom out to something truly dramatic happening in the cosmos. Scientists have captured the explosive end of a massive star in a scenario unlike anything they've seen before.
That's right, Avery. This event, more than 700 million light years away, began as a faint flicker. Within days, the light flared, faded, and then surprisingly flared again. It was completely unlike the standard playbook for dying stars.
What makes this even more incredible is that an artificial intelligence system flagged the event in real time. This allowed scientists to capture every phase of what may be the first recorded case of a massive star exploding as it tried to devour a black hole companion. Talk about cosmic drama. This supernova, named SN 2023 ZKD, was first spotted in July 2023 by the Zwicky Transient Facility, and then analyzed by a team from the Center for Astrophysics at Harvard and Smithsonian MIT. Their findings, published in the Astrophysical Journal, provide the clearest evidence yet that such extreme binary interactions can actually trigger a stellar detonation. It was part of the Young Supernova Experiment, a project designed to catch these exploding stars in their earliest stages. The AI system gave astronomers a crucial head start, allowing them to follow the explosion in near real time from both ground and space observatories.
Alexander Agliano, the lead author of the study, stated that their analysis shows the blast was sparked by a catastrophic encounter with a black hole companion, providing the strongest evidence to date that such close interactions can indeed detonate a star.
The leading explanation is that this massive star and black hole were locked in a decaying orbit. As they drew closer, the black hole's immense gravity pulled gas from the star into a surrounding disk. This intense stress is believed to have triggered the explosion before the star could fully engulf the black hole.
Another possibility is that the black hole completely shredded the star, with the debris collisions then powering the supernova's light. In either scenario, the aftermath left behind a heavier black hole.
What really stood out to astronomers were the unusual light patterns. From Earth, SN 2023 ZKD initially looked like a normal supernova, a single burst of light followed by a gradual fade. But then, months later, it did something truly extraordinary. It brightened again.
Archival records showed that the system had actually been slowly brightening for more than 4 years before the explosion, a rare and telling sign of pre-death instability. The analysis revealed that the supernova's light was shaped by layers of gas shed by the star in its final years.
The first brightening came from the blast wave colliding with diffuse gas, while that second peak was fueled by a slower collision with a dense disc-shaped cloud. The structure and timing of these events strongly point to extreme gravitational forces from a nearby compact object.
It's clear that AI played a crucial role here. As Gagliano mentioned, their machine learning system flagged SN 2023 SKD months before its most unusual behavior, which gave them ample time to secure the critical observations needed to unravel this extraordinary explosion.
V. Ashley Villar, a co-author and assistant professor of astronomy at CFA, added that this event shows some of the clearest signs they've seen of a massive star interacting with the companion in the years before an explosion. They believe this might be part of a whole class of hidden explosions that AI will help them discover in the future.
With new observatories like the Vera C. Rubin Observatory soon scanning the entire sky every few nights, and projects like the Young Supernova Experiment continuing to identify new events quickly, astronomers expect to catch more of these rare and complex explosions in action. It's truly a new era for observing the most extreme cosmic events. That's an incredible story of cosmic violence and detection. Now, let's shift gears a bit and delve into a long-standing cosmic mystery, the case of the universe's missing sulfur.
It sounds like something out of a detective novel. For years, scientists have been puzzled because there simply isn't as much sulfur floating around in deep space as they expected. This is quite an enigma considering sulfur is the 10th most abundant element in the universe and crucial for both planets and life.
Exactly. But a new international study might have finally found its hiding place. Researchers from the University of Mississippi, the University of Hawaii at Manoa, and Georgia State University teamed up to search for answers, publishing their findings in Nature Communication.
So, where has all the sulfur been? The team's results suggest that it's not actually missing at all. Instead, it's locked away in solid forms, bound within icy grains of interstellar dust.
In these frigid environments, sulfur atoms can arrange themselves in two main ways: neat 8-atom rings called octasulfur crowns, and chains of sulfur atoms connected by hydrogen known as polysulfons. These structures literally stick to icy dust grains, essentially freezing the sulfur out of view.
It's fascinating how a common element on Earth, found in volcanoes and power plants, can be so elusive in space. Ralph Kaiser, one of the lead researchers, explained that the observed amount of sulfur in dense molecular clouds is 3 orders of magnitude less than predicted gas phase abundances. That's a huge difference.
Astronomers typically identify elements in space by detecting the unique patterns of light they emit or absorb, while tools like the James Webb Space Telescope can easily pick out oxygen, carbon, and nitrogen. Sulfur just doesn't follow the rules in the same way. As researcher Ryan Fortenberry noted, when you do that for sulfur, it's out of whack.
Another challenge is sulfur's shape-shifting nature. Fortenberry likened it to a virus, always changing shape as it moves, making it incredibly difficult to track. But this new research points to stable molecular forms that astronomers can now specifically hunt for using advanced radio telescopes.
By recreating the conditions of deep space in laboratory experiments, the researchers confirmed that these solid sulfur compounds could indeed form on icy surfaces. And here's the key. Once these icy grains are heated in young star systems, the sulfur can sublime, meaning it transforms directly from a solid to a gas, making it finally detectable from Earth.
This work could finally help astronomers piece together sulfur's role in both the formation of planets and the very chemistry that supports life. If they can pinpoint exactly where sulfur is stored, it could deepen our understanding of how essential life-building elements are distributed across the cosmos, and even improve models of planetary atmospheres, especially for exoplanets.
It's a perfect example of astrochemistry forcing hard questions and leading to creative solutions, as Fortenberry put it. This kind of foundational research has the potential for significant, unintended positive consequences for our broader understanding of the universe.
That's a great point, Anna. Speaking of profound insights into how celestial bodies form, our next story completely redefines what we thought we knew about Vesta, one of the largest objects in the asteroid belt. For years, astronomers viewed Vesta as almost a miniature version of Earth, something between a rock in space and a full-fledged planet due to its rocky surface, distinct layers, and volcanic history.
But new research is truly shaking up that view. Data collected from NASA's Dawn spacecraft, reanalyzed years later, is rewriting our understanding of how early planets may have formed and what might have gone wrong in Vesta's case.
The Dawn spacecraft orbited Vesta from 2011 to 2012, meticulously mapping its surface and measuring its gravity. Initially, this data suggested Vesta had undergone planetary differentiation, the process where dense materials sink to form a core and lighter materials create a mantle and crust, just like Earth or Mars. Vesta's volcanic surface seemed to confirm this.
However, a decade after Dawn's mission ended in 2018, researchers at NASA's Jet Propulsion Lab, or JPL, decided to take a fresh look at the data using better calibration and updated processing tools. And what they found completely challenged that long-held belief. Vesta may not have a core at all.
That's a huge revelation. Ryan Park, a senior research scientist and principal engineer at JPL, expressed excitement, saying they were thrilled to confirm the data's strength in revealing Vesta's deep interior. By reanalyzing the Dawn data, the team made a more precise estimate of Vesta's moment of inertia.
For those wondering, the moment of inertia is a physics concept that reveals how mass is distributed within a rotating body. Assistant Professor Seth Jacobson of Michigan State University explained it with a simple image. Think of a figure skater. When they pull their arms in, they spin faster. When they stretch their arms out, they slow down. Celestial bodies with dense cores behave like skaters with their arms in, rotating differently.
And Vesta's behavior simply didn't match what scientists expected from a core-bearing body. Its moment of inertia, calculated at only 6.6% lower than a perfectly uniform structure, suggests its internal structure is surprisingly even. This value points to only a mild difference in density beneath its crust, not the deep layering we see in fully differentiated planets.
This new perspective has forced scientists to rethink everything they thought they knew about Vesta's formation. They're now exploring two main ideas. The first is that Vesta began to differentiate. Its insides started to melt and separate into layers, but something interrupted the process. This could have been a late start in forming or limited exposure to heat-producing elements, like radioactive aluminum-26.
The second theory is even more dramatic. It suggests Vesta might be the shattered remnant of a much larger differentiated planet. That body could have been destroyed in a massive collision during the solar system's early years, and Vesta would then be just one of the reassembled pieces, essentially chunky space debris of a growing world that never quite made it. Seth Jacobson, who initially considered this idea a stretch years ago, now takes it seriously.
The mystery deepens when you consider Vesta's meteorites. Researchers have collected thousands of space rocks on Earth believed to have come from Vesta, and these meteorites look like they formed in a molten environment, showing signs of volcanic activity. However, they don't obviously suggest incomplete differentiation, which creates a problem for the first hypothesis of partial melting.
That's quite the conundrum. The second idea, where Vesta is a remnant of a larger destroyed planet, might better explain the rocks, but it also raises new questions about how such a colossal collision would occur. Jacobson's lab is actively modeling what those collisions might have looked like and how debris like Vesta might have formed.
Ultimately, Vesta's internal structure holds the key to understanding how planets grow or fail to. For a long time, Vesta seemed like a textbook protoplanet, an object that started forming but didn't quite make it. Now, that picture has become much blurrier.
Instead of being a failed planet, Vesta might be something even more intriguing, a survivor of cosmic violence. If it truly is a chunk of a planet destroyed in the early solar system, it could provide scientists with invaluable insights into the collisions and processes that shape the world we see today.
As Jacobson puts it, no longer is the Vesta meteorite collection a sample of a body in space that failed to make it as a planet. These could be pieces of an ancient planet before it grew to full completion. We just don't know which planet that is yet.
This discovery is a powerful reminder that in science, answers often lead to more questions. This reanalysis of old data isn't just changing our understanding of one asteroid. It could reshape how researchers think about early planetary formation across the entire solar system.
And that's it for this episode. What a journey we've had today. From the surprising seismic activity of our moon and the critical implications for future lunar bases to the mind-boggling explosion of a star trying to swallow a black hole, the universe certainly keeps us on our toes.
Absolutely, Anna. And let's not forget the cosmic mystery of the missing sulfur, now believed to be hidden in icy dust grains, and the groundbreaking reanalysis of Vesta, which challenges its long-held status as a protoplanet, suggesting it might be a fragment of a destroyed world.
It's been a day packed with fascinating discoveries that push the boundaries of our understanding.
Indeed. Thank you for joining us on Astronomy Daily. We hope you enjoyed diving into the latest space news with us.
We look forward to having you back next time for more amazing insights from across the cosmos. Until then, keep looking up.